Okay, so refraction is the bending of light rays when it travels from one transparent medium to another transparent medium, and this reflection is generally caused by a change of speed. So now we are actually talking about the reflection of light lah. So what we can see is why it actually bends, right? It's because the light ray, when it move from one optically denser medium to another, there's actually an adjustment on the speed of light. Okay, and what this happen is that it will actually result in the bending of light. So one thing to take note that light reflection of light can also take place only if the medium is transparent, like your air, water, and vacuum, which is in space, glass, diamond, and etc. Now, the less dense, optically less dense the medium, the faster the speed of the light ray. Whereas the more optically denser medium, you will actually slow down the speed of the light. So in this case, right, what happens if you are moving from an optically less dense to a denser medium? Usually what will happen is the light ray will bend towards the normal. The normal in this case is the one in red. Okay, and we can see that this light ray, right, rather than it actually moving in a straight line, it actually bend towards the normal. And one example of this scenario, right, is actually your air and your glass, where glass is a denser medium. On the other hand, from a denser medium to a less dense medium, you would see that the light ray actually moves away from the normal. So this is typically from the glass to the air. Okay, and then light is reflected away. So there will be no reflection if the light ray travels in a perpendicular boundary to the boundary of the medium. So this is something like aligning it to the normal. So it just go one straight line. So this is in the event that it is 90 degrees to the boundary of the medium. A way to calculate the reflective index, right? So what is this reflective index? It actually just meant the ratio of speed of light in vacuum within the medium. So in a way, it tells us the material made, right? How will it affect the light? Okay, so that's where the reflective index is at. So you can use speed of light in a vacuum divided by speed of light in a medium. Now, the thing of speed of light in a vacuum, right, this is already constant for us, which is 3 times 10 to the power 8. So this C is something that you don't have to find the question, because it is something that you can remember. And this V is usually what you need to find in exam. So usually the exam, this is the one that you need to know how to calculate. And then this reflective index, it might be given from the question. You are not expected to remember the reflective index for all materials. This one is usually based on calculation. Okay, so it can be expressed in terms of also sine I over sine R. So rather than you having the speed of light in a vacuum over speed of light in the medium, it can also be equated to sine I over sine R. Now, what is this I and R? The I is actually the angle of incidence, whereas R is the angle of refraction. So angle of incidence, always remember, is with reference to the normal. A lot of students tends to have that misconception that the angle of refracted, right, it's over here. Now that is wrong. Okay, it has to be between the normal and the ray of interest. Okay, so sometimes we can, and so from this, right, we are able to actually use both of it to do the calculation. Now when it comes to the refracted medium, now do take note that the inner ray, right, is actually your incident, and the outer one is your reflected ray. So this is where you would have to readjust the reflective index, where it is actually 1 over n of sine I over sine R, or what we call as n equals sine R over sine I. This is in the event that you're moving from a denser medium to a less dense medium. A lot of students tend to have that misconception for these two. So always take note, first you check the optically denser, the medium is from where to where, then you use the respective formula. Okay. So one way I tend to remember is like I always put the less dense medium at the top. So the angle for the less dense medium should be at the top, So this is for less dense, and the denser one should be at the bottom. So this one again, if this one the top is actually denser, right? So I'll put the less dense here. And you could see that it goes in line with how the drawing. So actually, if you treat the plane mirror extension as a divide sign, you would have already be able to find the reflective index. So do take note that the reflective index does not have a unit because this, due to the ratio, they cancel out each other. But it indicates the light bending ability of the medium only as the ray enters the surface from air. Do take note that it's comparing between two medium and does not necessarily have to be air all the time. Okay, so these are some of the examples of the reflective index, which you can, if you want, if you have the bandwidth, you can go and memorize it. So that in exam, what will happen is you have a rough idea of where your answer is to check your working and things like this. Now, another thing is called critical angle. So critical angle is this angle of incidence which gives rise to an angle of reflection of 90 degrees. And what will happen is this critical angle, right, can eventually lead to something called total internal reflection. But before that, let's talk more about critical angle. So you can actually shoot an angle, a ray inside, and then you don't expect a bending. Instead, it tends to actually hit alongside with the plane mirror boundary. Okay, and this is where if it's just nice 90 degrees to the plane mirror boundary, the reflected ray, that's where there is the critical angle. So this will only take place from a denser medium to a less dense medium. Why? Because the light ray will tend to bend away from the normal. Okay. So the formula to determine the critical angle is sine C over, which is equals to 1 over n, where n represents the reflective index and C is the critical angle. So one thing to take note is because you are measuring from a denser medium, so reflective index equals to, what I can see here is less dense, so -90 degrees to sine C. Okay, and sine 90 is actually equals to 1. Sine 90 equals to 1, so 1 over sine C. And this is where your reflective index is n. That's how you actually get the formula where sine C equals to 1 over n. Okay, where 90 is your, this angle here, your angle of refraction. Okay, next is total internal reflection. So total internal reflection of a light ray at the boundary of two medium will happen whenever, what will happen is when your incident ray, right, is actually more than your critical angle. What this means is that this will actually cause your reflected ray to bend and eventually reflect inwards again, rather than pointing outwards. Okay, so this is where the light is actually incident from a denser medium to a less dense medium, and that the angle of incident is greater than the critical angle. These one have to remember in exam, as these are the two conditions for total internal reflection to happen. So total internal reflection is basically like, let's say you do swimming, you swim underneath the water, you realize you will be able to see your own reflection. Okay, so like the mirror, the water is actually like a mirror, but at the same time you are able to see outside because some of the area is not your own. You can you haven't hit the critical angle yet, so you should be able to see what is outside. Okay. Next, we look at optic fibers. So optic fibers is actually made of plastic and it works on the principle of total internal reflection. So in this case, what will happen? You have multiple internal reflection to help to pass the light ray or your information and things like this. So when light beam actually enters the plastic, it will be incident for a denser medium to a less dense medium, and these approach the boundary at an angle between greater than the critical angle. So they are very good because these optic fibers are very flexible, and their infra signals can actually travel around the corners in internally. So this can be used to transmit information to or from inaccessible places, mainly for transmitting signal in telecommunication. And since the total internal reflection takes place within the fiber, there is no loss of energy, and therefore it will be strong and constant even if the fiber cable is very long. So in a sense, how is this able to convert itself to like voice and what's not? It's because you see, right, every time you talk, right, this information is converted to light signals, like they turn on, turn off, turn on, turn off to represent maybe a sound frequency, and this is then transmitted along the fiber optics to another receiver and that is able to convert that into another sound. So that's one way in which your optic fibers can work. For internet, it can also transmit data, like your data, like your A can be 1001, those kind of hexadecimal, and due to the turning on and off of the light ray, you can actually see all these things. So the diagram shows the pathway of light ray passing through the glass block, and what you can see is this is actually an example of a total internal reflection, as there is internal reflection occurring. Okay. So that comes to the end of refraction. We will then the final segment is us talking about the thin converging and diverging lens, and then from there we can take a look